The title is The Local Global Principle for Stacky Curves.
Okay, thank you. Okay, so all that I will speak on is joint work with Manjul Bhargava. So let me start by reminding you some basic things about the local global principle for rational points on ordinary curves. So let's fix a non-negative integer g that's going to be the genus. So then you can ask if a smooth projective geometrically integral curve x of genus G, if it has so over a number field, K, so if it has a local point for over every completion, a KV point for every place, every non-trivial place V, must it have a K point? All right, so we know the answer to the converse. So okay, so the answer we know the answer to this too. So it's yes if G equals 0 as a special case of the Hasse-Minkowski theorem, and we know also that no if the genus is greater than or equal to 1. Okay, so but the point of this talk is to ask the question: what if we generalize the scope of the question to include Stacky curves? Well, I'll say what this means later. So what if x is a stack, and when you have a stack, it can have a genus that's a fractional value. It could be between 0 and 1. And so you can ask what happens for those intermediate values. Where is the crossover point between local global principle holding and failing? So let's consider G. So you can ask, precisely what we want to answer is what is the smallest G for which there's a counterexample, for which the local global principle fails. And I'll have to explain what all this means. Okay, fortunately, Cyril Demarche told you a little bit about stacks last time. I mean, he didn't give you the definition of stack. So the first thing I'm going to do in this talk is also not give you a definition, but I will try to give some more. In addition to what he said, I'll try to give you some more examples to give at least a feeling of what the ideas are and what kind of methods you can use to study them. Okay. All right. So I'm going to start by talking as an example. I'll discuss quotient stacks. So as an example, for which I conveniently have a picture right here, is if I start with a hyperelliptic curve, say y, and so this is the smooth projective model of some equation y squared equals f of x. So the real points might look something like this yellow curve. And so it has the hyperelliptic involution acting on it. So there's a group of order 2. So it acts on y. And so you can try to form the quotient. And if you're thinking of the quotient in the context of varieties, then the quotient is P1. That's that's the closest thing that any G invariant morphism to a variety would factor through. But that's not the true quotient. I mean, you can see that something funny is going on, because if you look at how the group acts, most of the points on the hyperelliptic curve are paired with another one, and so 2 points become 1 in the quotient. But then, if you have 1 point, that should somehow become half a point, and so with the true answer should be something like a P1, except with all the fixed points, they should be replaced by half a point. So I want to explain what this means, but that should be the true quotient. So this y should map to this true quotient, which is going to be the stack quotient, and that's going to be some sort of stacky, something that's birational to P1, but that has some stackiness in it. And then this will map down to this P1, and you can think of this as being some sort of ramified map, because above some of these points you have fewer preimages than you expected for a degree 1 map. All right. So more generally, you can take other quotients. So okay. If you start with if you're given y is any scheme, and G is some group, so group scheme acting on y. So you can form what one can define an algebraic stack so called y bracket y over G. So I'll put, well, essentially by specifying what its points are, for every scheme S. I'm lying a little bit, because the set of S points is really supposed to be a category, so you should not just say what the points are, but also what the morphisms between them, and they should all come in one big packet. No, I don't. It doesn't. No, it doesn't matter. Yeah. So, okay. So, all right. So what is? So what are the principles? Before I give you the definition of an S point, let me just give you some principles that guide the definition. Guiding. So first, so if T is another scheme with a G action, well then, and if you have an equivariant morphism, any G equivariant morphism, so any G equivariant morphism from T to Y, okay, so this is the G equivariant. That should induce, because that map is compatible with the G actions, it should induce a morphism of the quotient. So it should, so whatever these quotients are, you would expect to get a morphism like this. Yeah, and then there should be the quotient maps going down here. So there should be a square like that. Also, and the other principle is that any morphism from any scheme to this quotient should arise this way. From some T and some equivariant map. So with this in mind, I can give you the actual definition of an S point of this quotient stack. So for a scheme S, then if you take the morphisms from S to this Y mod G, what data do you need to give this? You should give a pair where T is something who's with a G action whose quotient is S. In other words, T should be a G torsor over S, and then there should be an equivariant map. So this F should be equivariant. So okay, so this should be a G equivariant morphism. Yes. Okay. So that's what the points are, and really this should be a category, but let me not get into that. And so this more or less tells you, this almost tells you what this, at least what this kind of stack is. And just as notation. Sorry. Yeah, you're completely right. I haven't told you what it's a category. I haven't told you what the morphisms are, but maybe you can guess what a morphism between two such things are. And it's a category in which all the morphisms are isomorphisms. And same thing here. The set of, but except that I do not take the you're really not supposed to take just the set of isomorphism classes. You're really supposed to. For the stack itself, you're supposed to allow the possibility of having objects. You want to remember the automorphisms that an object has, and not just, so that's, okay, but anyway.
Is the equality here correct? Is the set of morphisms exactly equal to, because then the cardinality is enormous. You can reproduce a T definitely. So.
Yeah. Okay. Yes. I'm using my braces in maybe an answer. Maybe by this I mean the category of morphisms, not the set of morphisms. But actually, what you say is actually maybe more appropriate for my talk, because the first thing I'm going to do is I'm going to take the isomorphism classes in this category and define that as my set of. Okay, I'll write this now. I'll say that x in the context for any stack, I'll define this to be the set of morphisms. Okay, I'll write this also. So this is with, and okay, these are the objects of some category, and then they're, well, the morphisms of morphisms. So okay. Anyway, here I will take the, if I want to speak about the A-valued points of a stack, where X is any algebraic stack, and which I haven't given you the full definition of, and A is any ring, commutative ring, then I will take the category. I'll take this set of things, or well, at least for this, and take the isomorphism classes in that. And that will be a set. So yeah, I'm sorry. It's not. Yeah, I really don't want to have to give the full definition of stack, because it would take a full hour. So okay. So okay. So another example is what's called a root stack. So for this, you imagine the following problem. So if you're given a scheme, so a scheme V, and an effective Cartier divisor. So it's locally principal. And a positive integer. So the question is, how can we modify V to replace this divisor on V by sort of a fraction 1 over n of d, in the sense that I have here, where I've taken p1 and replaced some of the points by half points. So what does that mean? That's the question. How do you make sense of this? So okay. Actually, the example sort of gives you a clue on what you're supposed to do. So imagine I was trying to reverse this picture, but I started with the P1. How would I make something that had those half points? Well, you would take that degree 2 ramified cover and then quotient by the mu2. So that's what we're going to do. So, okay, so this is the solution to this problem. Well, we're going to work locally. So that means, okay, so I mean, Zariski locally, and then glue at the end. But the advantage of working locally is that I can assume that V is affine, and that D is not just locally principal, but actually principal. And so in this case, so in this case I can choose a function, f in A, such that D is the divisor of that function. So D is the 0 locus, f is D is given by f equals 0, and then you can construct this quotient stack where you form the ramified cover of spec A of the original variety by adjoining an nth root of f, and then you almost undo it by taking this and quotienting by the action of mu n, where the action of mu n is where each element of mu n acts on this scheme by setting y to that zeta times y. Yeah, so you'll have the same. So most of the scheme will stay the same except for the places where y is 0, in which case you'll get that fraction. So as in that example there. Okay. All right. So now I think I'm ready to give you a sense of what I mean by a Stacky curve. So it's going to be something that looks like this. Okay, so a Stacky curve in this talk will be over a field K. Well, K is actually going to be a number field, the same as at the beginning. So it's going to be a smooth, proper. Okay, so all these. You have every right to complain because I'm not going to define any of these terms in the context of stacks. So you just have to imagine that they have some meaning that's analogous to what their meaning for schemes is. So one-dimensional. Well, and you don't know what this is at all because this doesn't even have a definition for schemes. It's not even well. I guess you know what Deline and Mumford are, but you don't know what this means. Okay, or maybe you do know. Well, if you do know, then you know. Okay, but anyway, I just want to, and I'll also assume, I want to assume that it's not the whole. I don't want the whole curve to be stacky. I don't want you to do something like take P1 and quotient by a group that acts trivially on the whole thing and make every point a stacky point. So I want to assume that there's a non-empty open piece of it, that's actually a scheme that has no stackiness. So isomorphic to a scheme. Okay, so I don't worry if these terms don't make sense. Let me tell you more concretely what these things look like. So at least over an algebraically closed field of characteristic 0, you can describe them as follows. So this X will look like, it'll look like a smooth projective geometrically integral curve in the usual sense as a scheme. So which is also called the coarse moduli space, the coarse space is associated to X, except that it has been made stacky by replacing finitely many points, say P1 through Pn, some geometric points, by replacing them by fractions of themselves. So replaced by I'll just write 1 over E1 P1. And you can use a different fraction for each one. And when I say replace, I mean in this root stack sense. So locally, this X is a root stack. So it'll be okay. So this is what it looks like, and for such a curve, you can define some of the geometric invariants. For example, you can talk about the topological Euler characteristic of such a stack. So let me define that now. Okay, so X is as there, and so the Euler characteristic is defined by taking the Euler characteristic of the coarse space. So you imagine we're trying to build this X. So we start with the coarse space. We remove the n points, and when you remove the points, you subtract 1 for each point removed, and then you put back 1 over ei of a point, some fraction of a point. And so, okay, so this is just a definition. This of course Euler characteristic. This is just 2 minus 2 times the genus of the scheme that you started with. So okay, so there's some definition. There are other motivations for this definition. You can also say this is what you need if you want the following formula to be true. Whenever you have a quotient stack where this is a usual curve. And this G is some finite group acting on it, a finite subgroup of its automorphism group. Then you would want to think of X, of Y as being a finite étale extension of X, and so the Euler characteristic then the Euler should be just the quotient. And so this is the formula that makes it true. It's okay. So. There are other motivations too. You can read. There's a nice article by John Voigt and David Zurich Brown. They go further and they talk about the canonical ring of such a thing as well. Okay. So anyway, so this is the other characteristic, and then if I want to discuss what the analog of a genus should be, then I will take as a definition just define it by saying that 2 minus 2g should be equal to this Euler characteristic. Okay, so let's see. So let's see. How am I doing for time? Yeah. So maybe there's an example. Maybe I won't do it in detail, but let me just mention quickly. There's an example that's implicit in the work of Darmon and Granville. I mean, they don't actually talk about it in the language of stacks, but essentially, this is related to the generalized Fermat equation. And so, if you take non-negative integers p, q, and r, what you can do is you can form the scheme. Well, start with this affine scheme over Z, where you write the generalized Fermat equation, and you view this as a subscheme inside affine 3 space over Z, but then you remove the 0 section over Z, and so the effect, let's call that S. So the effect of doing that is that now if you look at the integer points on S, the integer points on S just correspond to the points that are, you're removing not just 0, 0, 0, but you're removing anything that reduces to 0 mod 0, 0, 0 modulo any prime. And so by removing that 0 mod p for all p, it means all that you're left with are the primitive integer solutions, so the solutions to this equation where the GCD is 1. And so, yeah, so maybe I'll just write that. So S of Z is, so for this quasi-affine variety, this open subscheme of an affine variety, this is equal to the primitive integer solutions. To the equation, to this Fermat equation. But I mean, the nice thing you can do though with this, I mean, this is complicated because it's relative dimension 2 over Z, and so you can try to simplify it by exploiting its symmetry, by quotienting by automorphisms to get a lower dimensional object. So effectively, so what you can do, for example, is, well, I mean, this scheme has, this is in A3, so this is in A3 over Z, and therefore this has an action of GM cubed, just acting, it's just the diagonal torus, acting coordinate-wise. And so, but no, I mean, this whole group does not act on this. There's only a subgroup of you can define H to be the subgroup of this torus that preserves S. So it includes things like, well, I'll just say it includes the image of a one-dimensional torus where you take the transformations of the form where you scale in a weighted homogeneous way. So you scale like, so it's pretty clear that doing this scaling preserves the projective, or not, sorry, maps S into itself. But whether or not this group is equal to this is a copy of GM, but depending on what the common factors of P, Q, and R are, this could be larger. And sometimes H is it's not a torus at all. It's just a group of multiplicative type. But anyway, this H is the right thing to take the quotient by. in the sense that when you do this, when you form this stack quotient, it's always a one-dimensional group of multiplicative type, and you get this uniform answer that it's P1 with 3 of the points made stacky. So okay, so you get, so it looks like this kind of stack, and the proof of this, I won't do it in detail, but the key to the proof, the easiest way to see this is to quotient, instead of quotienting by this whole group, you quotient first by the following subgroup of H, where you just quotient by this, and then after you quotient by this, then there's an extra GM at the end to quotient by. And if you do the quotient in this order, you can see this quite easily. Okay, and then if you calculate the other characteristic for this, it's going to be 2 minus 3 plus all these things, so it's equal to this number. So this is essentially what Darmon and Granville observed without actually using the language of stacks. But and this leads to the statement. Eventually, you end up proving that the set of primitive integer solutions is finite and infinite according to the sign of this. Just as for so if yeah, so this is due to this, did I do something wrong? Oh, yeah, that is wrong. Yeah, okay, sorry. Okay. Yeah, otherwise that would, yeah, it's not that, it's interesting but not that interesting. Yes. Okay. Okay. Okay, and the same holds even if you put coefficients in front of here. Okay, so yeah, so I mean this, but the point is that this, it gives you other tools for studying these things. For example, you can use the descent method. You can start looking at finite tall covers of this stack, and that's essentially what Darmon and Granville do, and Boykers to study the solutions here. Okay, so this is just motivation, but you can see that actually for these kind of stacks, what's interesting is not. Well, let me say this. What's going to be interesting is not so much the rational points on these stacks, but the integer points. And the reason is that if you each of these stacks is birational to its coarse space, and so the rational asking whether x has a rational point is going to be the same as just looking at its coarse space. So to get interesting questions, we're actually going to want to look at integral points or S integral points. So yeah, so for now we're going to study integral points. And when we talk about local global principle, we're going to formulate it for integral points. Okay. So maybe I should say already in the Darmon and Granville paper, they gave something that can be interpreted as a counterexample to the local global principle. They gave essentially what is a stack of genus 2/3 that violates the local global principle. So we already know that 1 is not the critical value. So okay, so now I'm going to start talking about the new results. So I'm going to explain later. This is the minimal example. Okay, so now now things are going to get quite explicit. So I'm going to have primes P, Q, and R that are congruent to 7 mod 8, and satisfying some conditions. So these Legendre symbols should all be 1. And I guess you know what that means about the Legendre symbols if I turn them upside down. So yeah, okay. So, and let f of x, y be a binary quadratic form with so integral binary quadratic form of discriminant equal to minus PQR. Okay, so it's positive definite. Yeah, maybe I should say that. Okay, so positive definite. Yeah. Okay, and such, okay, positive definite. Yeah, positive definite. Positive definite. Okay, so, and also such that this leading coefficient, this A, satisfies some Legendre symbol properties as well. So A is a square mod Q, but A is a non-square modulo the other two primes. Okay, and by the way, these conditions can actually be satisfied. So what I'm going to write down is not an empty theorem. So okay, so if you don't believe me, you can check the following. Try these values. Okay. All right. I don't know if this is maybe not the smallest one, but anyway, good. Okay, and now take the conic defined by the following equation. So it's going to be inside P2 over Z. It's an integral model of a conic. So it's defined by this equation, by this quadratic form. Okay, that's not the counterexample. This is just an ordinary. I mean, it's a model for an ordinary curve. But now there's a mu2 that acts on this conic. If you have an element of mu2, you can let it act on y by changing the sign of z. So by sending each point on this projective scheme to you just multiply. So lambda squared is 1. So this makes sense. Yeah. So that's, and then well, you can probably guess what's coming now. I'm going to take the stack quotient of this projective of this curve by mu2. Okay, so all right, so that's the setup, and now what's the conclusion? Well, first of all, the conclusion is this is a stacky curve. I mean, if you look at this, what happens to this thing over Q, I'm just taking a conic and then quotienting by an involution. So I'm going to get some stacky genus 0 curve. Well, some stacky curve whose coarse space is genus 0. But this group has fixed points, so they're going to be. No, this is going to be it's projective because my y is projective. My curve y is projective. So when I take the quotient, the quotient will also be projective. This is inside. Yeah, I'm taking this equation inside. It's different from my previous the Darmon-Granville example. Here I'm starting with the projective curve, and instead of quotienting by a one-dimensional group, I'm just quotienting by a finite group now. So yeah. So okay. Okay. So. Right, so let's see. So what's the okay, so what's the conclusion? So then, first of all, x, so it is a stacky curve, and you can easily calculate its genus when you find that there are two fixed points for this action, and so what you get is a genus 0 curve with two half points on it, and that makes the genus it makes the Euler characteristic equal to 1, which makes the genus 1/2. And then you can check that it has local points, has a ZL point for all primes L, and also a real point. But it doesn't have any integer points. And even stronger, not only does it fail to have integer points, but it also fails to have integer points if you invert all the primes that you might think would be bad. So it still has no points over this ring. And if you know what a Deligne-Mumford stack is, then this is not, although the generic fiber over Q it's Deligne-Mumford, the whole stack is not Deligne-Mumford because mu2 is not an étale group scheme over Z. But if you really like Deligne-Mumford stacks, you want it to be Deligne-Mumford over all of Z. There's an alternative you can do. You can do the same thing, except there's another stack quotient you could take. You could take Y and quotient by the group scheme Z mod 2Z as a group scheme over Z, and have it act through where the non-trivial element acts by multiplication by -1 on the Z coordinate. So it acts through the homomorphism from Z mod 2Z to mu2. And then you can form that stack quotient as well. And it's going to have the same properties. You can check. This is, the fact that this holds. This is going to be the same for X and X prime because they're actually these two stacks are isomorphic once you invert 2. So you can check this. Okay. So anyway, if you want to do that, you can do that. All right. So let me now sketch the proof of this.
So in this case, in the previous case, you had an intuitive idea of where the points were, but now X of Z is this set of isomorphism classes.
Yeah. So it's hard to visualize what's actually. Well, I can tell you. Well, yeah, it's a little bit harder. Maybe this one is a little easier to visualize. But here, you're acting by something that. What are the fixed points of this action? If you quotient by this, the involution is x, y, z goes to x colon y colon minus z. But that fixes not only sort of the 2 points, the 2 sections. Well, geometrically, there's the locus where z equals 0, but also fixes all the points on the mod 2 fiber. So the whole mod 2 fiber is a Stacky mod 2 fiber. Yeah. Okay. Anyway, so I'm really only. This is only nice. This only looks nice over Q. Well, if you think of a Deligne-Mumford stack as nice. So. Okay. All right. So let me try to sketch a proof of this. Okay, I'm going to use the definition of what I told you earlier about what the S-valued points of a quotient stack are, and that's really the main. That will let me translate all these statements into something very down to earth, and it will just become a problem in elementary number theory then. Okay, all right, so here's a sketch of the proof. Okay, so I won't check the first claim about the genus. So I sort of told you why already. It was just there are 2 fixed points for the action. So, all right, so what does it mean to have an integer point? So by definition, that's the same as a morphism from spec Z to X, and X was this quotient stack. So it's a set of morphisms. And what does a morphism mean? Okay, so maybe I should say up to isomorphism. And yeah, so here, to give an isomorphism, what do you have to do? You have to give a torsor. You have to give a mu2 torsor over spec Z, and then you have to give a mu2 equivariant morphism from T into the original variety Y. And so it's these up to isomorphism. Okay, so in order to do this, I need to understand what these torsors are, the first step, but this is well known. So I'll have a little side calculation where okay, so let's see. So what is it? What are the mu2 torsors over spec Z? Well, those are classified by H1, and we're talking about FPPF torsors because this is an FPPF group over spec Z, and so of spec Z mu2, and this you can compute in the same way you do for a field. Using the commerce sequence, and so what you get is that it's the units modulo squares. I mean, I guess you know what these groups are also. And yeah, and this. I mean, the only thing I've really used here is the fact that the H1 of GM is trivial. So that's the class group. Yeah. Okay. So right, and you can make this very explicit. I mean, if you it works the same way as for fields. If you start with a number, a unit in Z, it corresponds to the torsor you get by taking essentially Z adjoin the square root of T. And if I want, but to make it work even when T is already a square, I mean, you formally adjoin square root of T. Okay, so that's what so these are what the T, the capital T, is going to look like. And then for each of those values, well, what does it mean to have a mu2 equivariant map from this one? And the mu2 here is acting by changing the sign of U. What does it mean to give a map from there into Y? Well, I mean, if you take all the maps from here into Y, that's just the Z adjoined square root of T points of Y. But to be mu2 equivariant, that means you want something that's not Galois invariant, but Galois anti-invariant. And so these so for each torsor, what you get is actually the integer points on the twist of Y, where YT is defined to be the same. It's just like Y, except you twist the equation by T. So by putting a T in front of the Z squared. So I mean, this should be very familiar to anybody who studied descent. It's exactly what would happen for any finite étale cover. So that that all the integer points are just the images of the points coming from the étale cover and all the twists. Okay, so this is what x of z is, and so there are only two of these things. There's t is either 1 or -1, and so you can just write down these things. You can easily check that neither y nor y sub -1 has any integer points. You just have to check that this quadratic form has no integer solution. So and you can do the same thing to answer the questions about whether there are ZL points or real points, because there's an analogous description of x of A for any, well, I mean, let's say for any principal ideal domain, A, B. I mean, the only reason I say that is just so I can use this fact again, that the easy description of this H1. So, but yeah, so okay, so then, well, you can imagine the rest of the proof. So let me just leave it with that. And there you can actually interpret this example, the non-existence of points. It also has something to do with genus theory. We haven't quite, actually, I don't really know if there's a genus theory over, is there a genus theory over the ring of S integers? Oh yeah, this is fine. Yes, yeah. This is. I'm just saying the whole theorem, or the non-existence of integer points. I'm saying can be deduced from some form of genus theory.
Here in this case, x of zn is not empty. I'm lost.
Oh, sorry. I'm saying this is a description of. So there. Okay. This is the part. So I'm saying that you can use this kind of argument to give a down-to-earth description of x of z, and you can give an analogous description of x of zl for any L. In this case, you have to check that these equations have the two equations that arise, they have no integer solutions. And so that's how you prove that x of z. And now for this one, you just have to show that one of the covering curves, one of these curves, one of these y sub t's does have z sub l points, except it's a different one for each L. There's no one of them that has zl points, and so together you know that the bottom will have a zl point, but they don't. You don't get a z point upstairs because they're coming from different sources. Yeah. Yeah. Okay. So So anyway, so let me leave that, and in the last few minutes, let me explain the complementary part of this. So this is just one example, but now for the hard part. So how do I know that this is optimal? Maybe there's a Stacky curve of even smaller genus that satisfies the local global principle, and so that violates the local global principle. So now I want to state the complementary theorem, so that actually verifies the local global principle for genus less than half. Okay, so here's the theorem. So and we do this we'll do this not just for Q but for any. We'll prove this for any number field, and we'll work not just with integer points but S integer points. It just seems more natural to do things this way. So S will be some finite set of places, okay, say containing the Archimedean ones, and so on. And so then you can define O to be the ring of S integers. Okay, maybe I won't. I guess you know what S integers are. So and then let me let KV be the completion of K at V, and OV will be the, well, for most V it'll be the valuation ring. The valuation ring in KV if for all the V that are not in S. And then for the just as a matter of convenience, let me just define it for the bad primes, for the ones that are in S. Let me just say I'll just take the whole of KV. I hope that's not too confusing. So for example, if V is a real place, then OV is real numbers. Okay, so okay, so now I need to tell you what kind of stacks I'm going to allow. I mean, it's a little bit technical because I really need to talk about these stacks over rings of integers, not just over a field. So it's a little more, it's not just a Stacky curve over a field as mentioned earlier. I mean, it's okay. So what is X? So again, I'm going to use all these words, but it's going to be a smooth, proper, irreducible algebraic stack. And by stack in this context, if you know what this means, well, I guess again you know what artin is. Maybe you don't, because there's more than one artin. But this is, I guess, Michael artin. Anyway, this is the more general kind of stack, not necessarily Deligne Mumford. And And it should be such that if you look at it over the generic fiber over the number field, then this should be a stacky curve in the sense that I defined, or at least described earlier. So, and I'm assuming that it has genus less than 1/2. And okay, so now the conclusion is that if it has an OV point for every v, then it actually has an S integer. Yeah, has an S integer point. Okay. All right. So the last thing I want to do is sketch the proof of this result. All right. So actually, just to simplify the notation, let me just for now. Although let me assume that let's just assume we're talking about O is just Z. So K is Q and O is Z. Okay, so the first thing is to say it's quite hard for a stacky curve to have genus less than 1/2. If you use that combinatorial definition of Euler characteristic I gave earlier, you can see. Well, first of all, this means that the Euler characteristic is greater than 1, and it's obtained by starting with 2 minus 2g and subtracting a bunch of stuff and adding some small fractions. And so you can just see very quickly that the only way this could happen is if the generic this stacky curve, it must look like this. It must be, first of all, the coarse space must have genus 0. The coarse space always has genus that's less than the stack itself. So it's going to be some genus 0 curve. So this is maybe I'll call the coarse space of that. And then you modify it by making some of this point stacky. But you can't if you start removing too many points and try to put in the fractions, you'll find that each time you make a point stacky, the Euler characteristic drops by at least 1/2. Because it drops by 1 and then adds at most 1/2. And so if you want to stay above 1 and you're starting with 2, you can't remove any more than 1. So it has at most 1 stacky point. So the only thing that makes the only thing that makes this theorem a little bit challenging is that we don't really. This only describes the generic fiber, and we're imposing very weak conditions on what can happen at the fiber's modulo primes, and so we somehow have to deal with that. Okay, so the next thing, I want to use the fact that this stacky curve has ZP points for every prime P. So this holds for all prime P, including infinity. So there's a real point as well. There's a morphism from X to the coarse space and to this genus 0 curve. And so this tells you that the coarse space also has a ZP point. For all P. And all P. Okay. And this is a proper curve. So this is the same as the QP points. Okay, but this is nice. We have a genus 0 curve that has QP points for all P. So we know at this point. So that tells you that this coarse space must actually be, this genus 0 curve must actually be P1 over Q. And then this stacky curve is just P1 over Q with at most 1 stacky point. And if there is a stacky point at all, it must be a rational point because it has to be Galois. Instead of stacky points has to be preserved by Galois. So you might as well assume that stacky point is at infinity. And so that means that this generic fiber, it contains a copy of A1, at least rationally over Q. Yeah. So okay, maybe I should put this on the same line. Okay. Anyway, so this is a consequence. And now, because everything is a finite presentation, you can say that if this happens over Q, it must already, in checking this condition, it only involves finitely many denominators. And so the same will hold over Z join 1 over n for some n, if you exclude some bad fibers. So this will contain a copy of the scheme A1 over Z join 1 over n for some n. And just for simplicity for this talk, let me simplify by, let's just assume, well, I could assume if n is equal to 1, then it's too simple, because then it contains A1 over Z, and then we know that that has a Z point. But let me make it a little bit more challenging for myself. Let's assume there's only one bad prime, just so I don't have to deal with so much notation. So this is Zn is just a single prime. And let me sketch how the rest of the argument goes. All right, so okay, I hope you don't mind if I use the forbidden board back here, but all right, so sorry, I'm a little bit over time, but I'll finish in a second. So okay, it has, and we know that it has at that bad prime. The thing we know is that the stack has a ZP point, and if it has one ZP point, and because it's going to have many, so many ZP points, and this is by some form of, this is essentially because it's smoothness. There's some version of, you can essentially use some version of the implicit function theorem. I mean, technically what you do is a stack by definition is covered by some scheme, and you can use the implicit function theorem there and deduce this. And so it has many points, including one that maps, one mapping into, that's not above the Stacky point. So one that maps into just the A1 part, into A1 of QP. And so we're going to look for points that are near that one. So what you could check, I mean, again, there's quite a few technical details in doing this, but if you look at the ZP points, that's going to be a subset of the QP points because X is separated. And then and what you can show is that this contains a non-empty open subset, say U, of this with its p-adic topology. And then by strong approximation, you can find a point in this copy of A1 that's defined over Z adjoin 1 over NP that also lies in this, that satisfies this p-adic condition as well. I mean, these are conditions. That's a condition all the primes away from P. Then you have this one p-adic condition at P. And so then, okay, so then now you have a point that's both a 1 over P point, and it's it's also because of the way U is defined. It's also a ZP point, and now so well there, and then there's, well, this might look obvious, but this should be, well, it should be then in the intersection of these two, it should be a Z point. But I mean, there's quite a bit hidden in this because there's some kind of descent because, well, I mean, really, you have to go into the definition of algebraic stack to lift everything to some algebraic space that covers it and argue it. And you actually do this with the Henselian ring instead of the complete local ring, and so on. But anyway, this is essentially the idea. And so let me leave it here. And so thank you for your attention.
Thank you. So are there any questions?
Besides the existing integral points, can you also discuss the approximation, for example, for these existing points? And
You mean weak approximation?
yeah, as well.
Oh, I haven't thought about that, but yeah, probably that you could do something like that sounds like an interesting thing to explore. Yeah, that's a very nice question.
So any other questions? Yes.
Somehow I knew that you were going to ask this question.
Yeah.
And I mean that's also something I think worth exploring. I mean I believe there is a notion of Brouwer group that you can define, but I don't know much about it. So it wouldn't surprise me, for example, if all these counterexamples were explained by that seems likely to me. In fact, maybe. Well, okay. I don't know.
Okay, so Matthew.
I have one. So for the Z-mod2 or mu2 action, you choose the trivial action on P1, meaning that if F has some symmetry, for instance, if A equals C in your equation, you could also switch X and Y. You see what I mean? Make Z-mod2 or mu2 acts non-trivially on P1 and also by -1 on Z.
Okay.
Could you say something in this case? Or because it's like the you see what I mean?
You're taking P1 over Z.
So for your
and
equation,
then you're looking at the automorphism that does this.
Yeah, and then on your equation x, y, z, such that z square equals f of x, y, you could if a equals c in f, like it's ax square plus bxy plus ay square.
Oh,
you could,
okay.
see what I mean? To use some non-trivial action plug in.
So you're taking a correct form that looks
for instance,
this one, and maybe
then
take z squared minus this, and then do as in our counterexample, except for this.
Exactly, and then you make some action on the P1 stuff,
And then you take this thing, and you take the quotient by this.
By this and -1 on z also, yeah.
You want to take a group of order 4?
Yeah.
Okay.
No, just -1, just -1 on z, but then permute simultaneously. But you do both. You both things. Just.
Okay. Yeah, you could do this. I don't
know. Because then, I mean, I think it would change. It would be interesting also to maybe.
Yes, I guess so. We haven't tried that, but. And one funny thing is that when you take a quotient, if you start with something whose genus is less than 1, and you take a further quotient, the genus actually goes up because the Euler characteristic is going towards 0, which is genus 1. So.
So any other questions? Okay, so let's thank the speaker again.